In this video, we continue talking about the graphical sensitivity analysis, and we consider the case of changing a constraint's right-hand side here. Alright, so we are looking at the same heavenly pouch example. We know that the optimal solution is located at the point C. And now let's consider a situation when we change the right-hand side of the third constraint, which is the budget constraint. We change it from 2000s to 2000s plus delta. All right, so this is our line that we are looking at here. So what does changing the right-hand side of a constraint mean geometrically? First of all, the coefficients of the variables are not changed. Therefore, the slope of the line is going to be the same. But the intercepts are going to change because the right-hand side is different. So if we increase the right-hand side of this constraint, then geometrically this corresponds to moving this line up. If we decrease the right-hand side, then it will correspond to moving this line down in this direction. All right. So now, when we make this move, how do we affect the optimal point for our LP? Our optimal point is located at C. And how is point C defined on the first place? Of course, point C has particular coordinates that we computed before, so it's the optimal point, right? But how did we compute these coordinates? We determined them based on the fact that the point C is on the intersection of the second and the third constraints, right? And this is how every corner of our feasible region is defined. It is defined by the intersection of the binding constraints at that point. So essentially, by picking two non-basic variables in our simplex iterations, we decide which corner of the feasible region we are going to obtain as a result of the iteration. For example, by setting the slack variables for the second and the third constraint to 0, meaning that we set them as non-basic variables, we obtain point C, which is our optimal point. So, to summarize, every corner of the feasible region is defined by two non-basic variables, and this is how we are going to treat the corner points now. We are not going to associate them with the coordinates, but rather with the two lines that define that point. Okay, so because now the lines are going to be moving, so when we change the right-hand sides, the coordinates of the intersection points are going to change. So when we say a point C now, what we mean by that will be not the particular coordinates of the point C, but the fact that we are talking about the point on the intersection of the lines corresponding to the second and third constraint. Similarly, let's say the point B will be defined by the intersection of the line where x1 is equal to 0 and the second constraint, and so on. So every corner of the feasible region is defined by the intersection of two lines defining our feasible region. So now, having agreed on what exactly we mean by point C here, so it's the point on the intersection of the lines defining the second and third constraints, what happens to this point C when we change the right-hand side of one of these constraints? So let's say if I keep increasing the right-hand side of the constraint, then the line is moving this way, and the point C, the intersection of the second and the third constraint, is gonna move to the right towards the point I. Okay, and what determines whether this point C is still optimal? So let's say if I make this move right here, so slightly to the right in the direction of I, will the new point C be optimal? Yes, it will still be optimal because our isoprofit line is still sandwiched between the two lines defining this point C. And this is our optimality criterion, right? A corner point will be optimal if the isoprofit line passing through that point is sandwiched between the lines defining that point. Okay, so it belongs to the cone defined by these two red lines. And this is still the case as long as C is feasible. So the only way the point C is not going to be optimal is if it becomes infeasible. So let's say at this point C converges to I, and C and I will have the same coordinates, and both C and I will be optimal at this point. And you see, in this case, we have three of the defining lines intersecting at this point. So this is the case of what we call the degeneracy, right? So in the degeneracy case, we see that not only non-basic variables are equal to 0, but some of the basic variables are equal to 0 as well. And remember what was happening in the degeneracy case. We would make an iteration, but we would essentially still stay at the same point. And this is exactly what is happening geometrically. So you have more than two intersecting lines at that point. Therefore, when we pick the non-basic variables, this can be done in several different ways, right? So we have three intersecting lines at this point, and any two of the corresponding slack variables taken as non-basic will define a different basic feasible solution. But effectively, all of these basic feasible solutions will correspond to the same point. So that was the problem with the degeneracy, right? We would switch the bases, but we would essentially stay at the same point and would not move. And in particular, when we have three lines intersecting in the same corner point for a two-dimensional problem, this point will correspond to three different basic feasible solutions, but effectively, again, it's the same point, right? So what is the third point? So we saw that C and I would be two of the points converging here, and the third point is gonna be on the intersection of the third constraint and the first constraint. Because look, we have first, second, and third constraints intersecting at this point I now, after we move the third constraint up to here. And look, when we were moving this third constraint towards I, the point of intersection of the first and the third constraint was given by D. And see what happens to this point D when we move the third constraint toward I. It's gonna move up along the first constraint, and it will also converge to I. So with this move, we'll have three of the points C, D, and I converging towards the same point, which is originally I, okay, and all of these 3 points will represent different basic feasible solutions corresponding to the point with these coordinates here. So let's see what delta value does this move correspond to. To determine the value of delta, all we need to do is plug in the coordinates of the point I in the left-hand side of our constraint, because now our constraint passes through point I, right? And when we plug in the coordinates of point I, which are 150 and 300, we will obtain the new right-hand side for our third constraint corresponding to this move. So we have 4x1 plus 5x2 at the point I is gonna give us 4 times 150 plus 5 times 300, which is 600 plus 1500, 2100. And original right hand side was 2000, therefore delta corresponding to this move is given by 100. And clearly, if we increase the right hand side over 100, then this is what is gonna happen. So we will go to the right of the point I, and we can see that after that, the point C, which is on the intersection of the second and third constraint, is not gonna satisfy the first constraint anymore. So the point C is going to become infeasible, and the optimal solution is gonna stay at that point I. Alright, so the optimal basis changed from what we had before when point C was optimal to the new optimal basis. So the highest increase in the right hand side that we can afford so that the previously optimal basis will still remain optimal corresponds to delta equal to 100 or the right hand side equal to 2100. So this is what we have done so far in summary. So we assume that the right hand side of the third constraint changes from 2000 to 2000 plus delta, and geometrically such a change corresponds to a move of the line on parallel to its original position. So this line would move, and if delta increases from 0 up, then the point C is gonna move right toward I, which corresponds to the total budget of 2100. So this is obtained by plugging in the coordinates of the point I, which are 150 and 300 in the left hand side of our constraint, and we can see that the right hand side then is going to become 2100. This corresponds to the delta level of 2100 minus the original right hand side 2000, which is 100, and then increasing delta over 100 will make the point C, which is on the intersection of the second and third constraint, infeasible because it's going to be to the right of I and the first constraint will not be satisfied. Therefore, this was the highest allowable increase of the right hand side of the third constraint, such that the previously optimal solution still remains feasible and thus optimal. Alright, so and we should observe that the previous optimal solution will always remain optimal as long as it remains feasible, as long as the change in the constraints doesn't make this point infeasible. And we saw that the changes done to the right hand side of this constraint, in order for the point C to become infeasible, it needs to move further past I along the line corresponding to the second constraint when we increase the right hand side of the third constraint. So now that we determine the highest possible increase for delta, let's see what will be the lowest possible delta for which we still have C as the optimal point. So in this case, we are going to decrease the value of delta from 0 to a negative number. And this will correspond to our line moving down, and the point C is gonna move to the left. So you see the point C on the intersection of the second and third constraint is gonna gradually move to the left along the second constraint, and it will remain feasible until we reach point B. Alright, so when C converges to B, this will correspond to the maximum downward move for the right hand side of our constraint, such that C still remains feasible. If we keep decreasing delta past this point, then our point C is gonna be outside of the feasible region, and obviously it cannot be optimal if it is infeasible, right? So to determine the lowest possible value of delta, what we need to do, we need to plug in the coordinates of point B in our left hand side here and see which right hand side of our constraint is going to correspond to. So the coordinates of point B are 0 and 300. So for point B we have 4x1 plus 5x2 is gonna be 4 times 0 plus 5 times 300, which is 1500. This corresponds to the value of delta equal to negative 500, right? So because 1500 minus 2000 is gonna give us negative 500, so delta is negative 500, and this is the lowest possible delta, such that when we change the right hand side by that value of delta, the optimal basis still remains the same. Now we can conclude that delta is between negative 500 and 100. So when delta stays within this range, the optimal basis corresponding to the point C will still remain optimal, and this corresponds to the right hand side of the third constraint going between 1500 and 2100. And it should be noted that when we are within this range here, the optimal basis remains the same, but the actual optimal solution is gonna change because the coordinates of point C do change. And then in order to obtain the new optimal solution, though, all we need to do is to just plug in the new coordinates of the point C in the objective, and this will give us the new optimal objective value. So to summarize, when we decrease the value of delta from 0 to a negative value, then C is gonna move to the left towards B, and when delta is equal to negative 500, then both C and G, which is on the intersection of the line corresponding to x1 equal to 0 and the third constraint, so both of these points are going to converge towards the point B. And at that point, x1 star is equal to 0, x2 star is equal to 300, so that's your new optimal solution, and z star is equal to 7500. And if delta is less than negative 500, then C becomes infeasible, and we concluded that delta equal to negative 500 is the lowest we can go without altering optimality of the previously optimal basis. So we obtain the allowable range to be between negative 500 and 100 for delta, or between 1500 and 2100 for the right hand side of our constraint. To conclude, let's consider another simple example of changing the right hand side of a constraint. In this case, let's look at a constraint that is non-binding at the optimal point. More specifically, let's look at the demand constraint, which is x1 is less than or equal to 350, so it's shown in red on this plot. If we try to alter the right hand side of this constraint, then clearly moving it to the right, which corresponds to increasing the right hand side from 350 to a higher value, is not going to impact the optimality of the point C in any way. Okay, so the allowable increase is actually plus infinity. On the other hand, if we try to decrease the right hand side of this constraint, we can see that it is not going to influence the optimality of the point C until it actually cuts the point C out of the feasible region. So if we go to the left of the point C, then this will make point C infeasible, and it cannot be optimal anymore. Then the lowest we can go with the right hand side of the demand constraint will correspond to the x1 coordinate of the point C, which is 125. So our optimal solution was 125, 300, and having the left hand side of 125 for the demand constraint corresponds to the delta value of 125 minus 350, which is negative 225. So we conclude that the range of right hand side for this constraint is 125 to plus infinity, and the range of change given by delta is gonna be given by negative 225 to plus infinity.